All right, so let me just try to draw a few boundary lines here. And then don't do it here. All right, I can't complain, saying words. Okay, any questions about today's test? Sorry about all the distractions. So today's test will cover up to section 5.4, okay, 5.5, and afterwards would be on test number 6. So we started chapter 6 yesterday. So we were talking about a square matrix of size n by n and a vector x which is strictly non-zero such that a times x equal to some scalar lambda times the same vector x. So you're just scaling that vector by some constant quantity. Okay, you call lambda as the eigenvalue of x, eigenvalue of the matrix A, and x to be the eigenvector of the eigenvalue lambda. So it's a pair. Every eigenvalue has a corresponding eigenvector. Okay. So we just mentioned that we didn't do any calculations yesterday. So let's try to work through a few simple examples just to show what exactly we are trying to do here. Remember that this is a n by n matrix. This is a n by 1 vector. And don't forget this is a number. Okay, that's a scalar. And that's also a n by 1 vector. So right now there is a little bit of a mismatch between what we have on both sides of this equation. Okay, that's a matrix, that's a number. To make things more compatible, what I'll do is I'll multiply the identity matrix on the right hand side so that you have a matrix on both sides. Okay. The identity matrix is just the equivalent of 1 in the world of matrices. So multiply the n by n identity matrix so that the right hand side also looks kind of compatible to operate together with the left hand side, so that both sides are n by n. Once again, if you're wondering what gives me the right to multiply this matrix on the right hand side just by itself, that's because this is equivalent to the number 1 in multiplication for matrices. You can always multiply 1 anywhere, it doesn't change anything, so just that's the same purpose here. All right, so we have a times x equal to lambda times I times x. So both sides have now matrices of size n by n. Sorry if you cannot see the, let me just and bring this to the left hand side, you get ax minus lambda I times x equal to 0. And you can factor out an x out of these two terms, so you have a minus lambda I times x equal to 0. So in other words, we are looking at the null space of this matrix a minus lambda I. So a is n by n, that is n by n, lambda is a scalar. Okay. So this is the null space of a minus lambda I, or we are trying to solve the homogeneous system a minus lambda I times x equal to 0. Not x equal to 0. So it's a newer matrix, but same concept. Well, all of you know that if you solve the system, there are two possible cases. Okay. So two possible outcomes here. One, there is a unique solution x equal to 0, which means there are no free variables. Okay. That also means that this matrix A minus lambda I is invertible. No free variables. So A minus lambda I is invertible. Now that sounds good in a typical problem, but then remember we are looking for a matrix or a vector which is not equal to 0. Okay. By definition, the eigenvector should not be equal to 0, and if this is what you're getting, that is of no use. Okay. So this is useless. Because x equal to 0 is always a solution. There is no point in writing it as a solution by itself. So the other outcome is that we have infinitely many solutions. That is what we are interested in. Okay. The unique solution in this case is pretty boring because that is just x equal to 0. We want to look at the case where there are free variables. In other words, this matrix is not invertible. And from the invertible matrix theorem, you know what that means. When you say that the matrix is not invertible, that means the determinant of this matrix should be equal to 0. So we have this n by n matrix, which is constructed from the matrix A and some scalar multiple of the identity matrix of the same size. Okay. This matrix should not be invertible so that we have an infinite number of solutions coming out of the system. So that is going to be our main setup there. Okay. The determinant of A minus lambda I should be equal to 0 to solve for the eigenvalues of the matrix A. And the reason why this is the starting step of this process is because we are looking for this particular case. All right, so let's see what happens with that. The determinant of A minus lambda I equal to 0. We'll erase this part here. So for a n by n matrix, that is going to give you an nth degree polynomial. Though we'll be doing problems with either 2 by 2 or 3 by 3 by hand, but in theory, this is going to give you an nth degree polynomial because it's an n by n matrix. Equal to 0, and that will give you n roots, which are the n eigenvalues of A. So we are trying to solve for lambda there because we know the matrix A, you know the identity matrix A. And when you set that up, you get a polynomial of degree 2, 3, 4, depending on the size of the matrix. And then to solve that equal to 0, you always get n roots, whether they are real or imaginary, that is going to depend on the matrix. Okay. It's always going to have n roots. And those n roots are the n eigenvalues of A. And for each eigenvalue, then you have to find what vector would make that true. So for each lambda, so for example, if you have a 2 by 2 matrix, you get 2 eigenvalues. For each of those eigenvalues, you have to find the null space of the matrix A minus lambda I to get the corresponding eigenvector. So it's a pretty routine calculation. Once you see it for a 2 by 2 matrix, it works the same way for any bigger matrix. Okay. Of course, there is no way of saying how difficult the polynomial is going to be. That's a different story, but it works the same way algebraically for any matrix of any size. So since I'm kind of working in the limited space, let me try to do some simple examples today to just make you get acquainted with this process. Okay. And I'll write the more trickier concepts on Monday when I hopefully get a bigger surface area to work with. All right, any questions about the definition of eigenvalues or eigenvectors, or why the determinant is equal to 0? Let me spotlight myself here. Okay, sorry. Any questions about this? All right, so let's look at the example we did yesterday as a motivational case. Okay, so let A equal to 1, 4, 2, 3. Find the eigenvalues and an eigenvector for each eigenvalue. So this example will show you what exactly happens during the calculation process. Okay, so the reason why the eigenvalues happen this way is all explained there. Now it's the calculation part, which is a pretty easy process. If you don't make any mistakes, okay, it's a very rewarding kind of problem. So you just need to be focused on what you're doing. So start with the matrix A minus lambda I, which when you see it for one example, you should be just able to replicate it pretty easily. Okay, so this is going to be 1, 4, 2, 3 minus lambda times the 2 by 2 identity matrix would be 1, 0, 0, 1. For a 3 by 3, it's going to be a bigger identity matrix, same process. And that's equal to, well, it's just the main diagonal elements which are affected here. So it's going to be 1 minus lambda, 4, 2, and 3 minus lambda. So we're going to set the determinant of this matrix equal to 0. Okay. And it shouldn't be surprising that for a 2 by 2, it's going to give you a quadratic equation to solve. So the determinant of this matrix, which is 1 minus lambda, 4, 2, 3 minus lambda, equal to 0. So when you're doing problems from the next example onwards, you don't have to write this matrix form like this and then go through the whole process. Okay, you could just start with the first step like this one here. It's always going to be the main diagonal elements subtracted with the lambda on those terms. The other two terms are not changed. Okay, so you could just start with this and just get going. There is no need to write these two steps here. All right, you know how to find the 2 by 2 determinant. That's going to be 1 minus lambda times 3 minus lambda minus 8 equal to 0. So let's simplify and solve this. So it's going to be lambda square. Then you have minus 4 lambda. It's lambda square. Then you have minus 3 lambda minus lambda. Yep. Then you have a plus 3 minus 8. Okay, that's going to be minus 5 equal to 0. I think it's easy to factor this than using the quadratic formula, or that's up to you. Okay, you could factor this as lambda minus 5 times lambda plus 1 equal to 0. So in this case, we have two real distinct eigenvalues. Okay, so you can label this as lambda 1 equal to 5 and lambda 2 equal to -1. Just for convenience, it doesn't matter which one you call as lambda 1 and lambda 2. Okay. All right. So that's the first part of the problem. Okay, find the eigenvalues. A 2 by 2 matrix will have exactly two eigenvalues always. Whether they are repeated or not, that's a different story, but it's always going to have two and exactly two eigenvalues. Okay, now we need to find an eigenvector for each of these eigenvalues. So which means you have to do two sets of calculations here, one for this and one for this. Okay. So for lambda 1 equal to 5, we need to find the null space of A minus lambda 1 I. So which means you have to write this matrix 1, 4, 2, 3. Lambda 1 is 5. So when you say 5i, that is going to be minus 5, 0, 0, 5. So subtract these two, you get -4, 4, 2, and -2. And all of you know how to do an REF for matrices of this kind. You can divide the first row by -4, second row by 2, and then you could do R2 minus R1. That's 1, -1, 0, 0. Now, here is one nice way to check your answer. Okay, if your eigenvalue is correct, there should be a row full of zeros always. Okay, if you don't get this, you are in trouble because there is no free variable. Okay, so this is a mandatory sign for a correct eigenvalue. If your eigenvalue is wrong, you're not going to get those row full of zeros, which means you are in trouble. Okay, that always has to happen. So that's a nice way to check your answer. You know that you are on the right track if you get those row full of zeros. Well, you're finding the null space of this matrix, so that's the basic variable. X2 is free. Okay. You can write x1 in terms of x2. That's what we've been doing for the last couple of weeks. So x1 minus x2 equal to 0. So x1 equal to x2. And you can call this as u. Okay. So x1 is u. So you're just kind of applying your skills with basic and free variables here in this 2 by 2 matrix. All right, so the eigenvector you get in this case would be x1, x2 equal to u, okay, which is u times 1, 1. Remember that u is a free variable, okay, so you have to exercise your right to pick a value for u at this point. Pick u equal to 1. Okay. Any value, what is the only constraint on that value? Any value which is attractive, or what kind of value should we pick? Let's make it even easier. There's only one number that you should avoid. What is that number? not zero. Okay, any value not equal to zero. That's the whole point of an eigenvector. You pick zero and you're making me very angry. Okay, so any value that is not equal to zero is good. Negative, you can pick decimal values if you are a fan of decimals, right? All right, pick u equal to 1, and that is what the question says, an eigenvector, which means there are infinitely many answers for this. Okay, we just need one of them. So let's call it as v1 equal to 1, 1. So if you pick u equal to 2, 2, 2 is an eigenvector. 3, 3, 3 is an eigenvector. All right, so can you find an eigenvector for the second one, lambda 2 equal to negative 1? So you just need to do the same process. Instead of 5, put lambda 2 here, which is a negative 1 there. Okay. So for lambda 2 equal to negative 1, not 1. Okay. This will be lambda 2. And since lambda 2 is negative 1, it's basically adding the identity matrix here. Okay. Negative of negative 1, it's plus 1. And you get 2, 4, 2, 4. You kind of know you're on the right track because it already looks like you're going to get a row full of zeros here. Okay. So you have 1/2 R1, R2 minus R1, whichever you want to do first, it's up to you. Okay. And you get 1, 2, 0, 0. Once again, x1 is free. Sorry, x1 is basic, x2 is free. So x1 equal to negative 2u, okay, where x2 is u. And plug it back into the eigenvector. So this is a generalized eigenvector here. So that's going to be u times negative to 1. Okay. Once again, there is nothing wrong in picking u equal to 1. Okay. There is no need to feel bad about it. So for u equal to 1, we have an eigenvector v2 equal to negative to 1. And that's a vector that I used yesterday for my demonstration. I showed you that when you multiply this vector by that matrix, it doesn't go anywhere else. It just goes as a negative of the same vector. So that is the process, whether the eigenvalues are going to be real, imaginary, or if it is a bigger matrix, the process is the same. Okay, so as long as the numbers are nice to work with, it's not a difficult problem at all. There are some concepts that I wanted to mention today, but since I'm working with a limited surface area, I'll postpone that to Monday. I'll just do one 3x3 example and then I'll stop for today. Sorry if I'm taking a little longer today because it took me some time to get started today. I'm sorry for the delay. But any questions about this one? All right, let's do a very easy 3 by 3. Okay. So 1, 2, 3, 0, 1, 2, 0, 0, 2. I'm purposefully keeping some zeros here because I want this to work out easily, and then on Monday I'll bring in some bad examples. Okay. Please don't do any REF on the matrix itself. Okay, you have to work with what you're given. The REF part comes for the eigenvector part. Okay, so please don't do any REF for this. All right, so let's start with the determinant of A minus lambda I. Okay. It's going to be 1 minus lambda, 2, 3, and that's what I said earlier. Just need to subtract a lambda from the main diagonal. Okay. 0, 1 minus lambda, 2, and 0, 0, 2 minus lambda equal to 0. You can expand this along the first column. That looks pretty attractive. So that's going to be 1 minus lambda times, so expand along first column. One minus lambda times this 2 by 2 determinant here. Let me just write it out. 1 minus lambda, 2, 0, 2 minus lambda equal to 0. Now, not all 3 by 3 matrices are coming out to be so nice. Okay, this is coming out nicely because of those zeros there. All right, just do this 2 by 2 and you get 1 minus lambda times 1 minus lambda times 2 minus lambda equal to 0. Don't expand it because it's looking in a nice form. Okay, if you expand it, you create a monster out of it. So just keep it in this form. If you have this product of these three terms equal to 0, that means the eigenvalues are going to be 1, 1, and 2. Okay, so there is a repeated eigenvalue here, which is one of the things we'll be highlighting next week. Okay. So 1 is repeated twice, 2 is not repeated, 2 is happening once. Okay, now we need to find an eigenvector for each of these. Okay. The good thing about repeated eigenvalues is that you only need to do it once for these two, because it's the same one. Okay, this one and that one is the same one. So when you have repeated eigenvalues, it saves time because fewer eigenvectors to compute. All right, to find the eigenvector or an eigenvector for each of those eigenvalues, again, you're looking at a null space of A minus lambda I. Okay, in this case, let's start with lambda 1. Lambda 1 and lambda 2 are the same, so there's no difference between those two there. And that's going to be 1, 2, 3, 0, 1, 2, 0, 0, 2. Lambda 1 is 1. Okay. Minus the 3 by 3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, that gives you 0, 2, 3. Uh, 0, 0, 2, and 0, 0, 1. All right, this is not fully in REF. Okay, so we could divide the second row by 2 and then do R3 minus R2. So let's do those. 1/2 R2, R3. You can divide the first row by 2 to make it strictly REF. Okay, so 0, it's 1/2 R1. 0, 1, 3/2, that is more of like a cosmetic thing. The second row is 0, 0, 1, and the third row is 0, 0, 0. So we are happy there is a row full of zeros here. Okay. If you don't have this, that's a big deal, because then we don't know what has gone wrong. Maybe you copied the matrix wrong or something has not worked out right. Okay. That has to happen. Now, which variables are basic and which ones are free here? If you look at this, it's a little bit awkward this time, because you see the first column is full of zeros. It can be a little bit misleading now. Which one is free, which one is basic? X1 is free. So ones with the leading ones are always the basic variables. So X2 is basic, X3 is basic, X1 is free. Okay. I've seen that whenever this happens, students seem to be a little bit confused about, oh, can X1 be free? Yes, it can be. Yeah. The whole point is that there must be a free variable, whether it's the first one, second one, or third one, we don't care. Well, let's now go to the matrix and solve for it. So row 2 gives you X3 equal to 0. Okay. Row 1 gives you X2 plus 3/2 X3 equal to 0. So X2 equal to 0. Okay. Remember, I told you that the vector cannot be 0. An eigenvector has to be a non-zero vector. It looks like we are doomed. X3 is 0, X2 is 0. What is my ray of hope here? X1 is free. Make use of the free variable. X1 equal to U. So X1, X2, X3 equal to U times 1, 0, 0. We cannot have these two guys here. Those are already 0. The only thing that you can somehow play around with is the first variable, which is X1. Okay. As always, you can set it U equal to 1 to get an eigenvector. Okay. All right, so set U equal to 1, and an eigenvector is V1 equal to 1, 0, 0. We only get one eigenvector out of these two eigenvalues. Okay, those are repeated, and it's not our fault. Okay, that is how the matrix works. So just one eigenvector for lambda 1 equal to lambda 2 equal to 1. Try to observe those things, because I'll be writing some statements about this on Monday, okay, about repeated eigenvalues and what kind of eigenvectors it comes out with. All right, and we had a third eigenvalue. What was that? 2. Or lambda 3 equal to, was it 2 or 3? 2. Just find the null space of A minus 2i. Okay. This is an ordinary eigenvalue. We don't expect any drama here. It's only with the repeated eigenvalues that sometimes things get a little bit crazy. 1, 2, 3, 0, 1, 2, 0, 0, 2, minus 2i is going to be 2, 0, 0, 0, 2, 0, 0, 0, 2. And so that is negative 1, 2, 3. The second row gives you 0, negative 1, 2. And the third one gives you happy face, 0, 0, 0. Nothing makes me more happy than seeing this. It's almost in REF, right? Just need to negate the first two rows. So if you want to write it here, you can write negative 1 R1, negative 1 R2. Just pass on the negatives here and here. Happy, happy. So here there is no confusion. X1 and X2 are basic, X3 is free. Okay. And if you go to the second row, you get x2 minus 2x3 equal to 0. Don't forget that x3 is free. Okay, that's your u. So x2 is 2u. And row 1 gives you x1 minus 2x2 minus 3x3 equal to 0. Okay. And that is u, that is minus 2u, so it's going to be x1 equal to 7u. So minus 4 minus 3. So the general eigenvector for lambda 3 equal to 2 is x1, x2, x3 equal to u times 7, 2, 1. Once again, pick any favorite value for u. Okay, so u equal to 1 will give you v2, okay, which is the only other eigenvector we can get here, which is 7, 2, 1. So that is the calculation part of eigenvalues, which just has this very repetitive kind of a nature. No matter how big the matrix is, it just has the same pattern. Okay. So you can start doing the homework after you're done with your test today. Okay. When you're doing your homework, just for the next couple of days, you can avoid the following words: okay. Algebraic and geometric multiplicities. I'll talk about this on Monday when I have more space. Okay. I'm not saying that these are not important. I'll talk about this on Monday. Okay. This and a few other trivia related to eigenvalues will be disclosed on Monday. But for now, you can just get started with the calculation part of it and get used to it. But if you are writing test 5, it's today, okay? And this is the last of the tests that you could drop if you want to mess around. Next week's test is mandatory. All right, sorry for the slightly extended lecture. So hopefully the camera will be back in action next week for 3 more days. Almost there. Okay, have a nice weekend after your test.
Thank you.
Thank you.
Thank you.